Hello, and welcome to Lecture 13, Part 2 of Life in the Universe. We're going to continue in our Unit E, Energy, Matter, and Light. And here we're going to look at a little bit more detail of spectra, in particular atomic spectra, and looking at the interaction of light and matter at the atomic level and how that lets us figure out what things are made of by analyzing the light we get from things. You'll notice that in a new environment here, I'm recording this lecture and the next one down in my basement. This one because I've got a demo a little bit later in here that needs to be dark for. And the next one because I'm going to be using something that makes an annoying sound and bother fewer of the other inhabitants of the house if I do it down here, I think. All right, so anyway, where are we? Okay, so right here we have an atom sitting in its ground state, minding its own business. And from the left, headed towards it, we have a photon, represented by the little wavy squiggle that I just circled. Now, if you remember back to what we had previously said about energy levels in atoms, let's say that the energy of that photon happens to correspond to the difference in energy between the ground state of this atom and one of its excited states. If that's true, then that atom can absorb the photon. The photon ceases to exist, but energy still has to be conserved. So to conserve energy, the atom jumps to an excited state. And in excited states, one or more of the atom's electrons are more likely to be further from the nucleus, which is why I put some of the electron, where is it, probability fuzz a bit further out from the nucleus here. Now, I don't think we're anthropomorphizing too much if we say that atoms don't like being in excited states. They want to be in the ground state. But to get back to the ground state, that atom has to give up some energy, and one way to do that is by emitting a photon. Now, it could emit multiple photons and get to the ground state in multiple steps, but if it does it in one step by emitting one photon, the photon it emits will have the same energy as the photon it originally absorbed, but it will be emitted in a random direction, not related to the direction from which the original photon came, and our atom's back in the ground state. All right, now we've got another photon headed to our atom, but this one has a different energy. And remember, energy and wavelength are correlated, so that's why I made this wavy squiggle a different wavelength. Let's say the energy of this electron, or sorry, this photon, energy of this photon does not correspond to the difference in energy between the ground state of the atom and any of its excited states. What happens in this case? Nothing. The atom stays in the ground state, the photon is not absorbed and is free to keep moving on its way. All right, so to summarize this with lots of words, atoms can only absorb or emit photons if the energy of that photon is the same as the difference in energy levels of the atom. Photon energy depends on wavelength, so that means that only photons of specific wavelengths can be absorbed or emitted by atoms of a given element. And since each element has its own set of energy levels, that means each element has its own specific pattern of wavelengths at which it can absorb or emit photons. I like to describe atoms as obeying Goldilocks rules of physics. Everything has to be just right. The mama bear and papa bear photons will not be absorbed or emitted, but only the baby bear photons that are just right. Now, here is an energy level diagram for hydrogen. So let's see if I can make legible letters here. So the ground state is down here, and then these higher states are the excited states, and this actually looks like a G and an E there, more or less. So upward arrows would be absorption, where we're going from a lower to a higher state. Downward arrows would be emission. We're going from higher to lower instead of lower to higher. Now, it turns out, and the numbers by each pair of arrows, set of arrows there, are the wavelengths of the photon that will be absorbed or emitted. if the for that particular transition. Now, it turns out that for hydrogen, transitions between the ground state and any of the excited states involve photons that will be in the ultraviolet part of the spectrum, so we couldn't see them by eye. However, there are some transitions between the first excited state, the second level overall, and higher states that are in the visible part of the spectrum. So there's that red line there. That transition is the turquoisey one. That one's that one over there. That one's that one there, and so forth. And then these others are in the infrared. So if we're going from higher to lower, that means we're emitting photons. So if we look at the light coming from atoms that are hydrogen atoms that are emitting light, and look at the spectrum, we'll just see a few bright emission lines like we see here. If we're going from lower to higher levels, say by sending light of all colors through a cloud of hydrogen gas, then we'll see absorption at the same wavelengths that hydrogen, when excited, will at which it'll emit. And so we see these dark absorption lines superimposed on that otherwise continuous spectrum. So let's think about kind of the details of what kind of spectrum we get to form in different physical situations a little bit more. So right here we have some hot light source. So that basically means just something that's providing thermal radiation. Basically could be any solid, any liquid, or any dense gas. And a wonderful astronomical example of this would be the interior of a star, as well as surface of a planet or something like that. Well, the interior of a star is going to be a lot hotter. Anyway, if we could take light directly from that hot light source without going through anything else, send it through a prism, look at the spectrum, then by eye, if it's bright enough, hot enough to produce a significant amount of visible light, then we'd see kind of a full continuous spectrum like that. If we do an intensity versus wavelength plot, we just get a continuous curve like that. And like I said, we call this a continuous spectrum. Okay, so that's over there. Now, over here, we've got that light going through a thin cloud of gas. Astronomical examples would be light from the interior of a star going through the thin gas layers in the outside. Could be sunlight coming in through the planet's atmosphere. Could be starlight going through an interstellar gas cloud. Whatever it is, some of the atoms in that cloud are going to absorb some of that light, but only at specific wavelengths, depending on the elements involved. So once we send that light through a prism and look at the spectrum, by eye, we'll see something like this with the dark absorption lines superimposed on what would be a continuous spectrum. And an intensity versus wavelength plot, then we've got these dips in the intensity at the wavelengths where the atoms in that gas can absorb the light. And so we call that an absorption line spectrum. So down here, we're now looking at light directly coming from that thin cloud of gas. So maybe just look light directly coming from an interstellar gas cloud without any bright stars behind it. Okay, so that light would be, as the excited atoms in that gas cloud try and get back to the ground state, they're going to emit photons, some of which will be coming down here. So we send that light through the prism, and by eye, we just see a few bright emission lines that we see here. And if we do the intensity versus wavelength plots, we just get some spikes of intensity at those wavelengths where those atoms are able to emit light when they try and get to lower energy levels. All right, now, the only reason this matters for us is if you remember that each element, as well as each ionization state of an element, even have its own set of energy levels. For isotopes, remember there are slight differences from one isotope to another. And in fact, molecules have different sets of energy levels than the elements whose atoms are making it up. Well, anyway, at the top we have a continuous spectrum, and then on the left we have emission spectra, on the right absorption spectra of a number of different elements. And if you don't, most of these you don't need to know, well, you certainly should know the bottom two, but you can look up what elements the symbols are for if you need to. But here's how we use this to figure out what things are made of. Say we look at the spectrum of a star, which typically will look like the spectrum we have on the right, but with lots more lines, because there typically be lots of different elements in the spectrum of a star. But let's say among all the lines that we pick out, we happen to notice this particular pattern right here. Okay, so that tells us that that star has barium, and a detailed analysis of how strong the lines are compared to others and so forth. We can figure out how much barium there is, but at least recognizing the pattern is enough to tell us that it contains barium. And I'm going to get out of the share here for a moment, maybe more for a moment. And so here is one of the reasons why I want to be down in my basement here, so I can show you something here after I turn the light off. So what I've got right here, this is a thing where I've got a tube connected to it. And this tube contains some hydrogen gas. And by turning this lamp on, I can use an electric current to excite that hydrogen gas. And as those excited atoms try and get back to the ground state, they're going to emit some light. And so first I'll turn it on here, and it's kind of bright, even with the overhead light on directly for the camera there. But I also have this. This is called a diffraction grating. It works like a prism, and then it separates things out by wavelength if I put it in front of the camera like that. But we need to kind of minimize how much other light we've got. So I'm going to stand up here so I can turn off the overhead light, and then wait for the camera to adjust here. All right, let's see. This is the orientation it needs to be in. Okay, and then there is some contamination here. Actually, it could even be coming from the lights on my headphones. And the spectrum repeats itself a couple of times. Right here's the primary one. Which actually you can't, let me see if I can get my finger for it. Okay, right here, there's that red line from hydrogen. There's the turquoisey one, and then you've got some more blue ones. And then this contamination is coming from somewhere, probably or possibly on the lights of my, on my headphones. So as you see, you've got the bright LEDs on there. Okay, now I'm going to pause the video for a second so I can switch the lamp so you don't have to watch that. So won't take any time. Oops, where did I go? There I am. Won't take any time for you, it'll take half a minute or so for me. So with no time. Okay, I'm back, and I've changed the lamp. So now it's got helium in it. And let's see, where's my grading? Where did it go? Let's see here. Okay, and you'll notice here that the pattern of lines, for it repeats again, is over here, is different than what you were previously seeing, and that's because the helium atoms in that tube have different set of energy levels. When they change levels, they emit different wavelengths of photons than was the case with the hydrogen gas in that tube. Okay, turn that out. Where is it here? There you go. Turn the light back on, just on the off chance you wanted to see me again, which you probably didn't. But anyway, as it turns out, I'll go back to the share here, just for a little bit here. As it turns out, helium was actually discovered in the spectrum of the sun before it was discovered on Earth. That's actually why it's called helium. So this particular pattern of lines was recognized in the sun as not belonging to any known element on Earth at the time. It was only later that it was discovered here on Earth. But anyway, this is how we can tell what things are made of by examining the light that we get from them. And that brings us to the end of this video and our attendant secret code, cave moose. And I'll stop the share so you can actually see cave moose here. I'm not sure where cave moose came from. The first time I was aware of it, it was down here in the basement. May have been a previous resident, the owner of the house had left it as a former dog toy or something. But I decided it's a cave moose because it's a moose, as you can see from the antlers. And I found it in the basement, which is the closest thing I've got to a cave. And you'll notice cave moose doesn't have any eyes. Now, the you might know that some animals that live in cave, fish, for example, that just spend their whole lives in cave, and some lizards, I think, and so forth. Because if you're in a cave where it's completely dark all the time, eyes aren't a very good advantage. Uh, and they're energetically expensive to build eyes. So some cave-dwelling animals have, through genetic mutations, just basically they don't make their eyes anymore. And so that's how I determined that cave moose is in fact native to dark things like cave. And that's why he lives in my basement, because it's normally the darkest place around. He probably doesn't like that I've got the light on overhead. All right, let's see here. There's probably nothing else on the video there. I mean, on the PowerPoint other than cave moose there. Is there code? Yep, that was it. So anyway, there is one more video for this lecture and one more to finish up this Unit E, which I'm going to record after we get Zoom to convert this and what it's just been recording into an MP4. See you shortly.